We're going to look at giant covalent structures in this video. So what I've drawn here is a methane molecule at CH4. And if you remember, carbon likes to form 4 bonds. So we've got 1 carbon there and it's bonded to 4 hydrogens. Hydrogen likes to form 1 covalent bond. So it's held together by covalent bonds, and it's like that tetrahedral shape. That's a methane molecule. Now imagine if you had the carbon, instead of forming 4 bonds to hydrogens, imagine if you replaced each of those with another carbon atom. Okay, so the carbon atom there, one there, there, and there. Okay, and then each of those carbon atoms, well, that would need to be bonded to 4 others, and so on, and the whole thing would build up. So you'd end up with that kind of structure. Now, carbon atoms covalently bonded in that way, that is what diamond is. That is the structure of diamond. And I've only drawn a really small section of a repeating structure. And of course, the smallest diamond that you could ever see, even with your naked eye, would contain billions of carbon atoms. Okay. And every one of those carbon atoms is forming 4 bonds. So you can see that, that carbon atom there, that is forming 4 bonds in my diagram. This one isn't. It's only forming 1 because that's at the edge. Because you remember, this structure carries on forever. So there's a relatively few carbon atoms on the edge, and most of them be like that one, in the middle, where they are forming that one there, where they're forming 4 covalent bonds. Okay, so that is the structure of diamond. Now, that is called a giant covalent structure. And whenever you get a question about diamond, you should always use those words. Say it's a giant covalent structure, giant covalent molecule. And it's interesting, when you pick up a diamond, you're picking up 1 molecule, because every carbon in that, billions of them, are covalently bonded to all of the other ones. So it is actually really is 1 molecule, and you can see it with your eye. Right, now diamond has got a very high melting point, about 3000 degrees C. And the reason for that is, if you want to melt it, you've got to break these covalent bonds. If you want those carbon atoms to be able to not be in fixed positions and move about freely, you've got to start breaking all of those covalent bonds. And covalent bonds are strong, and so you need a lot of energy to break them. So you need a very high temperature. A lot of energy required to break them. Right, let's contrast that to methane. Okay, so methane is a gas at room temperature. So I'll just grab a diagram of it down here. Right, so here, what I'm trying to show here is, right, we've got liquid methane on the left there. So the molecules are close to each other. And when you heat it up, you'll turn it into a gas. So all those methane molecules are a long way away from each other, and then moving about freely and so on. Now, you can see as you go from the liquid to the gas, you don't break covalent bonds. All of those covalent bonds are still intact. The only thing that you have to break are there's something called weak intermolecular forces. So weak intermolecular forces are just weak attractions between one methane molecule and another, sort of drawing them in green there. And they don't require much energy at all to break. They're really easy to break. And that means methane has got a very low boiling point. Now, there's a sort of classic wrong answer that people give to this question. A question will say something like, why has diamond got a low melting point, but why has diamond got a high melting point as methane has got a very low melting point? And the classic wrong answer, people tend to say things like, methane has only got weak covalent bonds. Now that is totally wrong, okay? That is completely wrong. The covalent bonds in methane, these are just as strong as the covalent bonds in diamond. But when you boil methane, do you have to break any covalent bonds? No, you don't. You're only breaking these weak intermolecular forces. So if we do a little let's do a little comparison, side-by-side comparison. I'll talk about what that thing is in a minute. Those two things there are other forms of carbon, which you probably recognize. We'll talk about them in a bit. But let's just do a comparison of giant covalent and simple covalent. Right, so giant covalent examples would be diamond. And we're going to look in a minute graphite, which is another form of carbon. Simple covalent is most of the covalent molecules you've ever heard of, so like H2O, carbon dioxide, methane, glucose. It's even got quite a lot of atoms in it, but it's still simple covalent. Right, how many atoms have you got in a giant covalent? You've got billions of atoms per molecule. Simple covalent, you've only got a few atoms. It may be as many as several hundred, but it's still that is not very many. It's not billions. Okay, or maybe even several thousands in polymers and things. Okay, now what else were you going to say about giant covalent? Right, if you want to melt giant covalent, you need to break covalent bonds. And that requires a lot of energy, so it's very high melting point. If you want to melt or boil simple covalent, you don't have to break any covalent bonds. You're only breaking weak intermolecular forces. And that doesn't require much energy at all. So they have low boiling points, low melting points. Okay, let's talk about the other form of diamond then, the other form of carbon, sorry. Right. So I'm going to move this one out of the way for a minute because we're not going to talk about that just yet. Right, let's look at this. This is graphite. So all of those black atoms, they're all carbon, okay? Now you may notice that each carbon there is only forming 3 covalent bonds, and we know that carbon normally forms 4. The ones on the edges are not forming 3, but all the ones that are, in the middle of it, like that one there, just circled, and that one, they are forming 3 covalent bonds. So that means there's a spare electron. So there's 1 electron which is not involved in the bonding, and that becomes delocalized. So it's not attached to any one particular carbon atom. It's kind of free, and it can move about. And that means graphite, the flow of these electrons, these delocalized electrons, is an electric current. So graphite can conduct electricity. If you apply a voltage to a piece of graphite, all the electrons will move towards the positive voltage, just like a metal. So it will conduct electricity very well. So that's an unusual property for a non-metal to have, that it can conduct electricity. All right, now you can also see that graphite exists in these layers of hexagons, okay? And although the atoms within the hexagons are covalently bonded between layers, so one layer, so that layer and that layer are not covalently bonded to each other, but they are held together by weak intermolecular forces, not covalent bonds. That's right, intermolecular forces. So that means graphite is slippery, because the layers can slide over each other. Because when you slide a layer over one layer over another, you're not actually breaking any covalent bonds at all. You're only breaking the weak intermolecular forces. And the graphite is what you call the lead in pencil. It's not really lead at all. It's graphite. When you write on a piece of paper, layers are sliding over, like layers slide off the block of graphite and the pencil onto the paper. And you can see the mark there. So that is a big difference, because remember, diamond, and you should always say, if you ask a question about diamond, diamond is not soft and slippery, it's hard. Because if you want to scratch a diamond, you have to break a covalent bond. Right, what about the melting point of graphite? Well, graphite has got a very high melting point, not quite as high as diamond, because there's only 3 covalent bonds per carbon rather than 4 in diamond, but it's very high, because if you want to melt it, you do have to break covalent bonds. It is a giant covalent structure. Right, now just while we're here, this gets to this sort of football-like structure here. This is another form of carbon, which it only was discovered in 1985, and it's called Buckminster fullerene. If you look at it, it's quite like graphite in a way, one layer of graphite. But if you look here, you've got hexagons, but each hexagon is also joined at that is not a hexagon, that's a pentagon. So you have a mixture of pentagons and hexagons stitched together, and that forms this curved structure. And there are 60 carbon atoms in this one. So it's sometimes called, see the formula down written, C60. There are actually bigger versions with like 80 and more carbon atoms forming slightly bigger spheres, which have been discovered as well. Now there's a lot of sort of speculation that these may be very useful molecules for doing things for using in the future. Most of those are kind of quite pie in the sky and kind of a bit science fiction-y, so I won't talk about them. But it's all part of the developing science of nanoscience. So nanoparticles are particles which are between 1 and 100 nanometers across, and 1 nanometer is equal to 1.0 times 10 to the minus 9, so a billionth. It's a 9 of a meter. Okay, before we finish up on giant covalent, I just want to go back to diamond, because there's another giant covalent molecule which is extremely common and is very similar to the structure of diamond. So I just actually what I'll do is I'll copy that. I'll put this down here. Okay, so there we've got our diamond. Now each of those are carbon atoms. What I'm going to do here is there's a molecule called silicon dioxide, SiO2. Now silicon is in group 4 of the periodic table, just like carbon, so it always forms 4 covalent bonds. And oxygen is in group 6, so that likes to form 2 covalent bonds. In silicon dioxide, all of those black atoms, these are silicon atoms, but also what you have between 2 silicon atoms, you have an oxygen atom. So that's forming, that red oxygen there is forming 2 covalent bonds, one to the top silicon, one to the bottom. So in every one of those, you're going to have an oxygen there. And if you draw the whole structure, the ratio of oxygens or silicons to oxygen is 1 to 2, so that's why it's SiO2. Now SiO2 is in sand or rock, okay, and it's just like diamond. It's very hard. It's hard to scratch it, because if you want to scratch it, you've got to break a covalent bond. It's got a very high melting point, because if you melt it, you don't just have to break weak intermolecular forces. So the atoms can move around, you have to break actual, sorry, I've left the oxygen out there, haven't I? And there. You have to break the covalent bonds, these covalent bonds, which require a lot of energy. Okay, so silicon dioxide, very analogous structure to diamond. Interesting, silicon dioxide's it's got a very high melting point, but it is less than diamonds. I think it's about 1500, whereas diamonds is about 3000. And that shows you that not all covalent bonds are very strong, but some are slightly stronger than others, and carbon-carbon bonds are stronger than silicon-oxygen bonds, so that's why the melting point of diamond is a bit higher than that of silicon dioxide. But nevertheless, the melting point of SiO2 is very high, because it is a giant covalent structure.